Hello, this is Mr. McMurray, and welcome to Chapter 8, Fluid Mechanics. Okay, the first thing we're going to talk about is what is a fluid, of course, because that's what it's all about, right? Fluid mechanics, okay? Fluids are in physics. Normally we think of fluid, bodily fluids, whatever, as liquids. But in physics, anything that can flow is a fluid. All right. So that means yes, liquids are fluids, but also air is a fluid. You feel the air flowing, wind, basically. Then that is also solids or not. Plasma could be, but we're not going to worry about plasma since that's not something we deal with on a regular basis most of the time, or it's in a contained TV or fluorescent tube or whatever. So we won't worry about that right now. But let's just talk about basically we're talking about anything that flows. So basically we're talking about liquids and gases. Okay, and when we talk about how fluids interact with each other, one of the first things we need to talk about is density. Okay, and density is an important principle, and we kind of understand it, but we need to know for sure. It's a measure of how compact something is. We talk about how heavy something is. Well, really, what we're usually talking about, if I have this lead weight right here, and I say it's really heavy, what I really mean is I'm saying, boy, I feel like a lot of weight in there. I could have something like a gallon jar that weighs as much or more, but it may not feel heavy. Why? Because it's spread out over a big area. This one has a lot of weight in a small little area, so that makes it very dense, okay, and very heavy. All right, it feels very dense. Now, density is the amount of mass compared to how much space it takes up, okay? If I were to cut a piece off, okay, which I have done, okay, right here, all right, of the weight, take a weight like this and I cut a piece off, which one has a greater density? Well, the correct answer is they're the same, okay? This one, say, has a density of, I forget lead off the top of my head, but 11.3 uh, uh, kilograms per meter squared or grams per centimeter cube. Okay, centimeter cube would be a centimeter by 1 centimeter by 1 centimeter. All right, but this one has the same density. It has less mass because it's a much smaller piece than this one. Okay, so it's a smaller piece, but it also takes up a lot less volume than this one. And so density is a measurement that does not depend on how much of it you have. The mass, yes, it depends on how much you have. The weight depends how much you have, also how much gravity you have. But density is a characteristic of it, and it's very often used to identify unknown minerals and rocks and so forth. Water has a density of 1. In other words, 1 gram per cubic centimeter, all right, or milliliters, 1 gram per milliliter. So basically, if we know how many grams of water we have, we also know how many milliliters we have because it's a 1-to-1 ratio. Okay, whereas lead, you have to multiply that by 11. Okay, because it has a density of 11.3 grams per milliliter or cubic centimeter. All right, how you want to look at that? Platinum is one of the most dense things. It's 21. It's even way more dense than lead. Mercury is 13.6. Okay, and ice is slightly less, 0.92. That's why it floats. And ethyl alcohol is even a little lower, 0.81. Okay, so anyhow, all those kind of things kind of give you an idea of some different densities. Okay, now something related to that, density is technically mass divided by volume, but to make it easier, sometimes we do weight divided by volume. Okay, which we know is proportional. If something has more mass, like this big piece has more mass than this little piece, then we know that it will also have more weight, same percentage more weight than this one. And so basically what we call weight density sometimes, just because it's easier to use the weight of something than it is, especially when we're talking about liquids, than it is to talk about its mass and density. All right, but keep in mind the density of any type of a piece of lead is going to have the same density, no matter how big or how small it is. Okay. All right. Now, another thing we have to talk about is the idea of pressure versus force. Okay. And let's see, just for a second, let's go back to our other one over here. All right. If someone were to come and say I'm laying on the ground for whatever reason, and a woman's carrying groceries, and she comes and she steps on me with these nice little flat sole shoes. Okay. The mass of the woman is the same regardless of what shoes she has, and there's a certain amount of force pushing down on me, her weight basically. All right, but if the same woman comes out wearing these high-heeled shoes, is that going to feel worse or better? It's going to feel a lot worse because all that force, same amount of force, same weight, but all that is coming down in about a square centimeter here and maybe a little bit here, whereas here that force is spread over a lot larger area. Okay, and when we spread the amount of force something has over an area, or how much force there is given per amount of area, that is called pressure. So even though the force of the woman stepping on me would be the same, regardless of what shoes she's wearing, because they weigh about the same, the pressure would be much higher on this one, and it would be very painful and cause bad things to happen to me wherever she stepped on me with these high heels. Okay, so basically, pressure has to do with the force and how it's spread out over an area. Okay, now the pressure has to do with the weight of something above. All right, which makes sense, and spread out over the surface area of me or wherever it's pushing on me at. Okay, so for example, if you were in the water, all the water above you would be pushing down on you, and that would determine the pressure of the water. Okay, and technically, it would also include what also is above you, above the water, is air. So you'd have the weight of the air pushing down on you and the water pushing down on you. All right, technically, we have air pressure pushing down on us right now. It's just like we're in an ocean or a lake of water or swimming pool. Same thing is true when we're in the air. There's all this air above us pushing down on us. Okay, and so and just the weight of that push to us. Okay, same thing. I'm talking about, but how much pressure depends on how that force is spread out over a certain area. All right. So, but when we talk about liquids, okay, or fluids, okay, we're talking about the density. It depends on how dense the air is above us or the water above us, and it depends upon depth. Okay, so this is a very important principle, and that is that pressure depends upon how deep we are in the liquid. All right, let's get to a place and we'll do some digital. All right, let's look right here. All right, I have a bottle. It's just a 7-Up or Sprite bottle. I don't remember which. And it has 3 holes poked in the side. I don't know if you can see that with the tape right there. Okay, 3 holes. Now, question is, if I take one of these off, what's going to happen? And the correct answer is not much. It dribbled out a little bit there, but basically nothing happened. Why? Because no air could get in to take its place, and water's trying to come out. The air pressure is trying to push it back on there. There's air pressure. Okay. Now, if I take another one off, whoa, it does come out. Now, I have 2 holes. Why does it come out this bottom one? That's a good question. But basically, because the bottom one has a lot more pressure on it. Hang on just a second. Trying to get that lid open. All right, before we lose too much water here. Okay. So, now if I take off this middle one, we have 3 of them now, you will notice that the bottom one is shooting way over here. The middle one is not going as far, and the top one, in fact, is pretty much quit doing anything because there's not enough depth right there. Okay. However, these 2 are still going good because they have a lot of water above them, therefore they have more pressure. This one right here, the middle one, is not going as far out. Why? Because it doesn't have as much depth of water above it. And the bottom one has a higher depth, so it's shooting way off over here. Okay? And so basically, how far the water shoots off is always going to depend on the depth of the water above it. As you go deeper and deeper in the water, you're going to have more and more pressure. Now, notice the pressure is also perpendicular to the wall. It's coming straight out. So the water's going down. Why? Because once it gets out of the bottle, then gravity starts pulling it, and it makes that parabola like we talked about. But you'll notice the one at the bottom is going a lot straighter. Why? Because it's going a lot faster, because of more pressure, and it has a lot flatter parabola. All right? But basically, it's shooting straight out. If we had a hole up here and it were full, it would shoot straight that direction. All right? Let's do another demo, and we'll try to demonstrate that. All right, let me just describe the thing before we try to fill it up here. Okay, this is a, looks like a long flask, but it has a bunch of holes at the bottom, and there's on the bulb for the round part, but they're in all different directions, okay? Then it has a plunger, okay, up here with a cork in it. So let's see if I can get this filled up, and then we'll do a demo with it. Quickly, I'm going to push on this and notice which direction they shoot out. All I don't know if you saw that there at the end, but there you see it's the end. Boom, boom, boom. Okay, they shoot out in all directions. Let me make sure you have to see that. A lot of washing up after this slab. Okay, all right. They go shooting in all directions. Why? Because each one of them goes perpendicular to the surface where the hole is. And so if there's a spot up here, it's going to go shooting up originally until gravity affects it, and it'll start going back down. Okay, if it's on this side, it's going to go perpendicular to that. If it's perpendicular, so the force is always applied perpendicular to the surface, and the more pressure is applied, the deeper it is. Here we go. Now we have a hose. It's continuous. I don't know if you can see all that down there, but yeah, it goes all the way through. All right, I have stoppers on each end, and you'll notice that with the stoppers on, I can turn it upside down. Nothing happens. They stay the same length. Why? Because there's air trapped in there, and the air pressure keeps the water from moving. But if I take these off, all right, the stoppers off, okay, now if I start moving one of them higher, this one goes higher, you'll notice that this one also goes higher. But you will notice that they're always going to be even with each other. If I leave this off, they're going to be even. Why? Because they're the same depth, okay, and therefore they have equal pressure. And so with the air pressure on top and the height of the water pressure being there, they're always going to be equal. All right. Now, if I were to take this one way up here and let go of this one right here, guess what? It would try to get equal. So it would try to rush up to get to this height. Unfortunately, I can't do that. So it would. If I can do this, I'll make a big mess of myself. And it goes shooting out the end. All right, so basically, we say water tries to find its own level. Why? Technically, it tries to equalize the pressure because the pressure depends on the depth. So they try to have the same height. It doesn't matter if I had curled this part up into curlicues or sideways, or one end got real big. It doesn't matter. It's about the height. Okay? The height is what causes more pressure. All right, now we're going to go talk about stuff on the board real quick because this is an important principle having to do with height and principle. Next thing we're talking about is buoyancy. When you put something in water, there's always a force pushing up on it. And we want to talk about real quickly why that's so, then we'll go demonstrate. Okay, so say I have a rock, a big rock. It's under the water. Okay, well, water exerts a force in all directions. Okay, so it's going to exert a force down on it. It's going to exert from the sides, from the very sides over here, and even from the bottom side. Now you could draw the same thing over here. I just don't have time for that. Okay, but you'll notice I didn't draw them all the same size. Why? Because pressure depends on how deep they are, the depth. And the top of the rock is not as deep as the bottom of the rock. Okay, and so if we were to put those together, so here's the one pushing up, here's the one pushing down, you're going to have that much different in pressure. Well, we know if we have two forces. If you have that much different in pressure or forces, we know it's going to go in the direction of the bigger one, so it has a force pushing up on it. Okay, that's one reason why when you do exercise in the swimming pool or whatever, it's less stress on you because you don't have to use as much force to hold your body up. This buoyant force helps push up. Okay, now since this part is always going to be deeper than that part, there's always going to be a difference in there. What happens if it goes even deeper? Well, the pressures get bigger. So let's just say this pressure, let's say it's twice as deep, so it's going to double. All right, but this one is also deeper than it was before, so it's going to have a little bit more. Okay, so it's still going to be, the difference between them are going to be equal. The difference between the pressure on top and bottom, which is how much is going to push up on it, is going to stay the same. So this is very important. As it gets deeper and deeper, there's more and more pressure, but the buoyant force on the object stays the same. Once it's completely underwater, the buoyant force stays the same. Why? Because the difference between the top and bottom, and it's always going to be about the same amount. Even though as it gets deeper and deeper, there's more pressure on top, there's also more pressure on bottom, and so the difference is still the same. Okay, let's look at an example and prove that does actually. Several things I want to show you here. Okay, first of all, we have a pool ball with a hole dug in the middle and a screw put into it. Very nice. Okay, and we have a spring scale. If we put this on and we look on the side that says grams, it will tell us that this one is about 90. Okay, I don't know if you can see exactly where that is, but it's about 90. Okay, but right there. Now, if I put it in this and it goes underwater, now underwater, and you can see that now this thing has a very low drag. It doesn't take much force at all to hold it up. What? That's that buoyant force pushing up on it. Okay? Now, that buoyant force is not as much as the pool ball weighs. So if it were not hanging on the scale, it would sink to the bottom because force of gravity or its weight is greater than that. Okay? But it's pushing up. And so now, if I read the scale, it only says it costs about 25 or 30. Okay? 25 or 30. So instead of almost 90 or 100, somewhere in there, it goes down to about 30. Wow, that's interesting. So there is a buoyant force, and it's pushing up on it, okay? And that's the difference between the higher pressure pushing on the bottom and the lower pressure pushing on top. And so it ends up with a net. That's why you always have a net upward force. Buoyant force is always upward. Now, this is a little handy thing. I had it full up to this little spout. When I put the ball in, it made the water leave or displace. We may have used this in probably in junior high and high school. You would displace the water, okay? And if you did this in junior high, you did this to find the volume of it, okay? All right. Just for the record, this thing weighs, we said, about 85 to 90, okay? But when we put it in there, it only weighed about 20 or 25, okay? Now, let's weigh the water that came out, and that will tell us the volume of it. Okay, and if we look at the volume of it, it says it's about 75. About 75. So it says, well, it's not as much as the volume of the ball is not as much as it weighs, and that's true. But the amount it displaced, let's take that 90 minus about 20, and we get what? 70. In other words, when I put this in there, it displaced 70 milliliters of water. And guess what? Instead of being about 90 grams, it only took about 20, or it took off about 70 because that buoyant force took off. All right? And this was Archimedes' principle, which is a very important principle it came up with. And that is that the buoyant force, which we know is because there's greater force in the bottom of it, is equal to the mass, not of the ball, but of the water that it displaced or moved out of the way. When you put something in the water, the buoyant force will be equal to the mass of the water that it scoots out of the way. Okay, so good question. What if I put a bowling ball and this one in water? Which one has a greater displacement? Think about that. All right, so here we are. We have a tub full of water. Isn't that exciting? Okay, now we have a beach ball, a kind of a giant golf ball looking thing. I think it's a softball, fakey thing. The pool cue ball, we have a ping pong ball, and we have a golf ball. Okay? Now, the question is, which one of these would have the greatest buoyant force, or would they have the same amount? Well, let's talk about just two things here real quick. First of all, we have a golf ball and we have the ping pong ball. Now, they're not exactly the same size. Let's say they were exactly the same size. Okay, which one would have more buoyant force? Well, if we drop the golf ball in there, it sinks all the way down to the bottom. I hope you can see that. All right, if I drop the ping pong ball, it floats on the surface. Okay, but the buoyant force has to do with the mass of the water displaced. Well, turns out if you put these in the water, if they were exactly the same size, then they would have exactly the same buoyant force. Why? Because they would displace the same amount of water. Now it would have to hold the ping pong ball underneath, but it would still have a buoyant force, and if I let go of it, it would come up to the surface. Okay, I don't know if you can see that very good, but it would come up to the surface. Okay, all right. The golf ball may have to continue to fall. All right, boom, bounce off the bottom. All right, now, so I have a beach ball, and I have the little golf ball, softball-y looking thing. Okay, which one of these has more buoyant force? Well, we know if we put this one underneath, it's going to bounce right back up. If we put the softball thing, it's just going to sink. Okay, but if we look at by size, this one has more volume, so it's going to displace more water. Therefore, that more water is going to have a bigger weight and mass, and therefore it's going to have a stronger force on it. Okay, notice stronger force doesn't have to do with necessarily whether it floats or not. Okay, in the first case we said, well, the golf ball had slightly bigger, so it has slightly more buoyant force, but it sunk. All right, whereas the ping pong ball has less buoyant force, but it still floated. Okay, opposite here, we have more buoyant force with the beach ball, and we have less buoyant force with the one that sinks. Okay, it's not the weight of the balls or anything like that. It is the amount of water they displace. So the bigger it is, the more displacement you have. Say you have a bowling ball and you have a volleyball. They're about the same size. They have about the same volume, and so they would have the same displacement or the same buoyant force pushing up on them. Okay, but once again, same force, but you have two objects with different mass is going to have different effects. Okay, and so even though the golf ball has more of a buoyant force than the ping pong ball, the force of gravity is going to, and the weight of the golf ball is stronger than the buoyant force, so it goes ahead and sinks. So whether something floats or sinks has totally to do with the buoyant force compared to the force of gravity or the weight on the object. In the ping pong ball, it doesn't even sink very far into the water. All right, there you can see it. Okay, why? Because when it displaces just that little bit of water, the weight of that water, that's the buoyant force pushing it up, is equal to the weight of the ping pong ball. And so it doesn't even sink very far. Things that float mean that their weight is less than the buoyant force. Okay, same thing with the beach ball thing. All right, it does displace some water, just a little bit, but once it does that, then the force of gravity is equal to the buoyant force, and it stops right there. Now with the golf ball and the softball thing, you could just keep adding, and I'll take that back. The softball one does float. But notice it just barely, I don't know if you can see that, but it just barely floats. Why? Because they're almost equal to each other, okay? And so the force of gravity, weight, is not as strong as the buoyant force, so it does float, but they're almost the same, so it just barely floats. Now, theoretically, if you could do this perfect, I hope you can see that, but I've got just a water bottle filled with water with a little bit of air pocket in it. All right. If you do it right, you could have what we call neutral buoyancy, where the buoyant force is exactly equal to the weight, and then it would just hover right here in the middle. You could let go of it in the middle, and it would just sit there. Okay, now this one's pretty close. If I hold it underwater and let go of it, but it will gradually come up. All right. Can it be done? Theoretically, yes, but I found it's a good thing for someone who just can't sit still in class, give them this to work on for a while because it's very difficult to do. All right, but in theory, if you keep adding water, you could eventually reach neutral buoyancy. Okay, now part of the reason this probably is not because the air in there is not mixed evenly throughout, so it doesn't have the same density. But theoretically, I could move this, if I get it right there, then I can just let it hover there. Okay, in fish, they have an air bladder that they can fill up with air, which makes them less dense, or they can get rid of it, and that makes them rise or sink. They can swim up and down, but most of the time they usually use that air bladder to make themselves rise or sink, and their fins are just there, and tail and stuff are just there to make them go forward. Right? But that's an important concept there. All right, now we've been talking about liquids. Let's talk about the other half of the fluid equation. Let's talk about gases, okay? Gases are not the same as liquids, obviously, and there are some differences, okay? So one thing that's different is if I put a liquid in the syringe, okay, and let's just say that I open it up a little bit more. Now there's an air bubble in there. The liquid is not going to swell out and fill in that whole thing, okay? However, on the other hand, if I have this container, don't worry about the balloon for right now. Okay, if I have this container, does it have anything in it besides the balloon? We normally would say it's empty, but it's not empty. If I put a stopper here and I try to blow up this balloon, I can a little bit, but not very much. Why? Because it's full of air. Okay. However, you notice it did fill up some. because I could increase the pressure on this side just enough that it would push there. Now, what happened to all the others in here? Did it go away? No, it's still there. It's just being squished closer together. And so in a gas, the molecules are far apart. They're constantly moving, and as they bounce around, they hit the walls, and we call that air pressure. Talk about your tire of your air pressure on your car or your bicycle. It has to do with how many molecules there are bouncing around inside your tire and putting that pressure on the outside, which keeps it aired up or keeps it from collapsing. Why? Because it's that pressure of all those air molecules bouncing around in there. Okay, so one, they fill the container. You can't just have half a jar of air. It's going to spread out to fill in the whole thing. Okay, they can move around a whole lot more. They can go in any direction, stuff like that. And that push, that pressure when they hit the sides of the container that they put on there, that the force when they hit on the edges is called the air pressure. Okay, but air pressure changes a whole lot more easily than water pressure does. Okay, if I have water, for example, all right, in my syringe, I have water. Okay, I can push on this as hard as I can, but I cannot squeeze that and make it more dense or take up less space. Why? Because the molecules are still pretty close together, and there might be a minuscule amount, but not even enough to be measurable. Okay, it looks like exactly like it did before. In fact, I've had people try so hard they just broke the syringe, but they don't compress the water. Okay, it's not compressible. But air, on the other hand, gases, okay, are compressible. So I fill this up to 20 milliliters of air, okay, and I can squeeze that down to about 5 milliliters of air. Is there any less air in there than there was before? No, it's all still there. It's just all crowded in small amounts. And so if I can increase the pressure, I decrease the volume. If I let go, I decrease the pressure, then it's going to expand and come back up here to 20 again. Okay, and so how much volume it takes up depends on how much pressure it is. Okay, and that's something we don't have to worry about with liquids so much. Okay, the other thing that's different is as you go higher up in the air gets less dense. Water is pretty much dense, same density, whatever, unless it has stuff mixed in it like salt water, which makes it more dense or something like that. But basically, water is equally dense. Anywhere in a lake you go, the water all has the same density. Air, on the other hand, is thicker down here at the bottom where we are. As you go farther up in the air, it gets thinner and thinner and gets to be less dense. Okay? And so we have to consider some of those things when we start talking about how air pressure affects us. All right. Right here you can see that we have a syringe. It's at the very top of it. It's got about, I think it's a 10 milliliter syringe. It has 10 milliliters of air in it. And it's at room air pressure, okay? But we got a pump. There we go. Fancy word there. I had to think it out. But anyway. Okay. All right. So now, as I pump air into this, what does that do to the pressure inside? Well, it increases it. Okay, it has a lot higher pressure. Okay, and it's gone from 10 down to about 5. You can see the numbers if it quits rolling. Okay, I have increased it. Why? Because if I double the pressure, guess what happens to the volume? I get half the volume. Okay, we're not going into a lot here, but it was in the lecture. I think Boyle's law says, assuming the temperature stays the same, don't change the temperature. Well, that has other things to do. We'll talk about next week. But the pressure times the volume before has to equal the pressure times the volume after. So if it was, to say, a pressure of 1 inside here, and it was at 10 milliliters, 1 times 10 gives you 10. All right, now that's only at 5, so that means the pressure must be twice or 2 compared to what, if it was 1, now it's 2. It's twice as much pressure because the pressure times the volume before has to equal the pressure times the volume after it. Okay, and so basically the more pressure I put in there, it's going to have an equal decrease in the volume of the actual air in there. All right. All right. Now, then the other thing is my pet here. I have a pet squid. Okay, and he's pretty good. I trained him to do tricks. All right. So, for example, I say, sing, go to the bottom. No. I said, go to the bottom. There you go. Very slowly. Oh, let's just stop and hover in the middle. Oh, he does. See, he's trained pretty good. And then I said, no, go back up to the top. Oh, he did. And then I said, oh, no, dive to the bottom real quick. All right. So basically, I have a trained squid. No, I don't. Okay, actually, this is a Cartesian diver, which basically is like a syringe up here with a bunch of red and yellow tentacle-y things hanging out the bottom. So it looks a little like a squid. But basically, how am I controlling whether it goes up or down? Well, first of all, it's full of water. So the density inside here is basically the density of water, or 1. All right, but inside that top part there's a syringe. All right, and I had squeezed most of the air out. There's still some air in there and water. Well, air with a little bit of water, kind of like that container, the little water bottle I had that had a little bit of air in it, would float to the top, is less dense, so it floats up to the top. However, if I squeeze on this and I increase the pressure, the liquid goes in there. It cannot compress, so it has to squeeze in there, and it squeezes that air into a smaller amount of space, which makes it more dense. Okay, if the whole thing is getting more dense, more water's going in, and so it's adding to the density, then it's going to start sinking. Okay, when I let go of the pressure, the air pushes the water back out of the syringe. Now it's a lot lighter than the water, so it's going to go up. Okay, now it's got to be pretty close to the density of the water, because I've got to be able to squeeze it enough that it actually makes it, even with a little bit of air in there, I can make it more dense than, and that's why I have to have the lid on too. I can make it actually more dense than the water, and so it'll actually sink. But then I let go, it becomes less dense as the water. As the air spreads out, takes up more space, it makes it light enough to come up. All right? All right, so that has to do with pressure. For air, just like we have water pressure, if you're under the water, you feel the weight of the water pushing down, gives you water pressure. Scuba divers deeper in the ocean going to have a lot more pressure, a lot more depth pushing down on it. Okay. Same thing is true of air. We're at the bottom of an ocean of air. We said it gets less dense and thinner as you go up higher, but it's still all being pulled by gravity toward the earth, and the weight of that is pushing down us all the time. Now, we don't think about it, but there are 5 pounds per square inch. So every square inch in your body, there's 15 pounds pushing down on you. Okay. So I don't feel it. Well, because you're used to it. Okay. If you came from some place where there was no atmosphere, like the moon, and you didn't have any air pressure because there is no atmosphere pushing down, then you say, wow, this really hurts. It's kind of like if you have a fish that lives down in the bottom of the ocean has all this pressure pushing down on him. But he's used to it. He's always lived there. If you pull him up to the top real quick where there's less pressure pushing on him, sometimes their bodies will actually explode out because they're not used to that less pressure. And they're trying to equalize the pressure and they end up blowing up. Okay, same thing. We have air pressure pushing down and we don't think about it. Okay. Now, a couple examples of air pressure. Let's talk about some of this. All right, this one here, one of my favorites, is just a flat sheet of rubber, and it has a little gasket in the middle with a hook on it, just so you have something to pull on. All right, and basically, if you pull up on it, I've never tried 100% to pull it up. I'm afraid I would rip the gasket out before I would actually lift it up. Why? But that's silly. It's just sitting there. It's just sitting on the surface. Okay, but every square inch on this has 15 pounds pushing down on it. And if you multiply that by the number of square inches here, it's about 144 times 15. That's a lot of pressure. And so it will do that. I have a hat that has a wide brim. Same thing. It will kind of stick, and the air pressure will keep it down. Now, there is the brim inside the middle of the hat has air in there trapped. So it's not nearly as hard to stand up. But in this case, there is no air on the inside. But if I lift up so it lets air leak in there, then it's really easy because now you've got the air pressure underneath it pushing up also. Remember, air pressure pushes in all directions. So we were saying that air pressure, just like water pressure, pushes out in all directions. So that's why an object in the water has water pressure pushing it on all. Well, air pressure does the same thing. If I have this container full of water and I have this little plastic sheet on top, and I flip it over, it will stay there. Why? Because the air pressure, not only pushing down on us, it also pushes back up. It pushes against the walls. That pressure works in all directions, okay? And that's what keeps this. Now, if I let break the seal, then all bets are off, okay? Gravity kicks in and takes over. But as long as it's sealed, the air pressure will push up on it, and as long as that pressure is greater, that 15 pounds per square inch is greater than the weight of the water, which in this case it was, then it will keep it up there and in place. Let's look at another example of air pressure that you have no doubt done in the past at some point. Okay, and I have a straw, and I'm going to use it here. Okay, normally stick straw in there. When I suck on the straw, I'm sucking air out, which makes a vacuum. Lower air pressure. The air pressure pushes down on the liquid and pushes it up the straw because there's lower air pressure there. All right, but if I poke a hole in it, I can suck as hard as I can, but I can't hardly get any liquid to come up. Why? Because I can't lower the air pressure. When it's solid, I put my finger over the hole here, then when I suck air out, that lowers the air pressure, and the air pressure on the outside pushes the water down and pushes it up the straw. But if I let that go, as I suck air out, more air comes in and takes its place, and I have equal air pressure inside the straw as I do outside the straw, and it doesn't go anywhere. Okay? Now, scientists have used that same kind of principle to make a barometer to measure air pressure. Okay? Now, they don't use water, they use mercury, but obviously if I'm going to use mercury, that's going to be kind of dangerous. So I'm not going to do that. Okay? Now, I'm going to try this. Let's see if I can do this without making a mess. All right. In order to measure this, I get a test tube. I get it completely full of water, and then completely put it underwater, and I turn it upside down. And you will notice that, maybe you will, maybe you won't. Hopefully you can see that. The water is still in the test tube. There's no bubbles, no nothing. And no matter how far down or up I put it, the water is still stuck in there. Why? Because the air pressure is pushing down on the surface of the water and will not let it come up. If I take it out of the water, all the water rushes out. But as long as it's underwater in the fluid, then the air pressure pushing down keeps it there. Okay? Now, water is not very heavy. And so in order for, even though the air pressure is, there's not enough weight to pull the water down. Okay? But if I could do this, we could do it, but you'd have to have one about 36 feet tall or something like that. Okay, if we had a test tube 36 feet tall, well, that's not very practical. So what they did is they got something heavier. They put mercury. So there's mercury down here, mercury in the tube. They turn it upside down in the mercury, and that's how the barometer actually works. The air pressure pushes on the mercury. If there's more air pressure, it pushes it up. If there's less air pressure, it goes down. But there's room for it to go up and down because mercury is so dense. Okay, very heavy. Even though the air is trying to push it back up, it usually comes down a little bit, and therefore it can go up or down depending if the air on the outside pushes it down, or if it pushes less on it, it sinks down. We talk about the mercury rising and falling, and that's what we're talking about, air pressure. And that's important because, generally speaking, if there's a lot of moisture in the air, it's less air pressure, and so the lower air pressure means there might be rain. High pressure areas, like we just had in July, obviously, we're going to have October a little bit. Means that there's going to be hot and dry, okay? Because high pressure is not moisture in the air, it's not hot. Okay? That's how they use this to measure it. All right, just one more demonstration using this bottle since I have it. You might as well use it. Let's say I air it up. Okay, well, obviously, if I let the air out, it goes right back down, right? But let's try this. If I put the stopper in the bottom so no air can come in to push it out, guess what? It will not deflate. Why? Because there's no air pressure to push it out. Okay, but as soon as I take this off, I let outside air pressure come in, and it pushes the air out on the elastic balloon. Okay, but another thing is suction. Okay, we talk about suction a lot. Technically, there is no such thing as suction. That's the number one thing I want you to know. There is no such thing as suction. Suction doesn't exist. Suction technically is a difference in air pressure. That's all it is. There's one side has more air pressure, the other side has less. There is no such thing as suction. So, oh, but I know there is. Okay, we saw that rubber mat a minute ago, right? It had suction. You couldn't pull it up off. Okay, and then if you broke the suction, you let air in there, it would come up. No, what we did is we equalized the air pressure. Okay, if you look at my drink over here, it looks like it's just sitting there. Well, actually, it is sitting there, but it wants to remain sitting there. Okay, why? I can't pull it up. Why? Because it has this little collar around it. Okay, and I have pushed all the air out. So there's no air pressure on this side, but there's still 15 pounds per square inch on the outside. So that's still going to be 20, 30 pounds of air pressure pushing this down. So if I hit this, it's not going anywhere. Okay, that's a very effective thing for a very simple thing, but it's going to keep it in still as long as I don't break the seal. Now, if I break the seal, that allows 15 pounds per square inch pressure, and it pushes in all directions, including up, and then I can pick it up very easily. Okay, but it's not because it has suction. Suction means one side has no air pressure and the other side has a higher air pressure, and so it works. Okay, we're talking about arrows and darts and things that people used to shoot each other's kids. Well, these are some suction cups. Well, they're not. They're pressure differential cups. Okay, if I squeeze these together, okay, if I just set them together, whoops, it's hard to put them together without doing it. Then they come right apart. Why? Because there's 15 pounds of square inch pushing out and in all directions, so it's easy for it to come off. But if I push it and it lets the air go out, okay, then there's no air inside. So now we have air pressure on both sides pushing from the outside in, and so it stays together. All right. Now if I put a little air in there, then I got 15 pounds per square inch pushing out as well as on, and they come right apart. Okay. Now why do some people lick them? Well, because it seals better and it keeps air from leaking back in. Okay. All right. We say it's for better suction, and it really does. It keeps the air pressure less on the inside. Now these are called Magdeburg spheres. The ideal ones are made out of iron. They put them together and they suck all the air out. But these have a little thing here, and if we turn this handle, it pushes the air out. So I push this one and I push this one, and if I push it on there, I can't do it. You can't do it. We could have two people here and they could fight, but they're probably more likely to break the handles off than they are to get there. Why? Because the air pressure on both sides or inside is 0, and on the outsides is 15 pounds per square inch, and basically they're not coming back. They actually had some of the metal ones, they actually get teams of horses and try to pull them apart, and they could not do it. Okay, so it's very effective, but that suction is really just meaning that there's less air pressure on one side and more air pressure on the other side. All right, all right. We don't really have any things for pascals, pressure and fluids, but you do need to make sure you notice that in the notes and check that out. Let's talk about buoyancy in air. Air is a fluid. It also has buoyancy and Archimedes' buoyant force acting on it. In other words, this displaces a certain amount of air, and there's a buoyant force equal to the weight of the air. All right, and so there is a buoyant force putting up on this, but if I drop it, it's going to go down. Why? Because the weight of the plastic is greater than the air inside it, and it just displaces air. The plastic and the air of the ball, the balloon or the beach ball, is going to be more dense than just plain air, and so it's going to sink. Now, if I were to fill this with helium, which is much lighter than air, then the helium and the plastic might have a lower density than just plain air, and it would actually rise. Okay, but same thing, the buoyant force depends on, they would have the same buoyant force either way, whether it was full of air like it is now or it's full of helium, because it's going to displace the same amount of air, so you're going to have the same force pushing on it. But if it's full of helium, then that force is going to be greater than the weight of the beach ball, whereas if like this, it's going to be less than the weight of the beach ball. The force of gravity is going to be greater than the buoyant force is going to be less than the weight of the beach ball, which is going to make it sink. Okay? All right, so there's that. All right, one last thing with air is important is Bernoulli's principle. All right, and the principle of Bernoulli is, the idea is, well, first of all, you can take a little piece of paper if you have one at home. If I blow across the top of this, you think, well, what's it going to do? Well, it's going to blow it down, right? Or let's see. Nah, didn't do very good. Okay, hang on. Ran out of time. Okay, if you blow across a piece of paper, it will actually come up. Why? Because when air is moving this direction, it doesn't have time to push down. In other words, when air is flowing, it doesn't have time to push down on it. Okay, so for example, if I take this, all right. Okay, hang on. Anyway, I'm sorry, I'm not very good. We're running out of time, but okay. Say I have this toy that you may have seen before. Okay, I'm going to blow out the pipe. And okay, well, the air should exert a force on the ball, and the ball will shoot out, which is kind of true, but it doesn't go. Why? Because as the air swirls around it, it's going really fast around it. There's less pressure, and so there's more force pushing down, and so it kind of hovers up there, kind of trapped between the upward force, but it's moving fast enough that there's less, and so it doesn't just keep on going. It hovers right there where it meets kind of an equilibrium. All right, and if we wanted to do that a little more bigger scale, we could take this. Take our full cube. So with this, let's try it. And it will, not much, but it will stay just right about this surface. All right? And that's Bernoulli's principle. All right, make sure you read the notes for that. Otherwise, don't forget that you have article coming up, and you have your quiz and so forth. But Monday through Thursday next week, you need to take your tests next week. Okay, so chapter 2, exam 2, over 5, 6, 7, and 8. One last demo on Bernoulli's I forgot about. Okay, now if I were to put this up there and just blow air into this bag would take a long time to get it to blow air out. Okay, take a lot of lungs full of air. But using Bernoulli's principle, if I just blow here, that means the air is moving faster, which means it has less pressure, which means other air will rush in to take its place. Let's see what happens. And in 2 breaths, I can inflate the whole thing. Why? Because the air flows over. It doesn't have as much time. It has lower pressure, which air from the side rushes in to take its place, and that creates an airflow that goes through there. It's the same basic principle that causes as the air flows over one side of the wing, it has to go farther, so it has to go faster, which means there's less pressure pushing down, and that gives the airplane wing lift. All right, that's it. Promise not anymore. All right, have a good week.